Hello guys, today we're going to be covering section 2.5, which is going to be on continuity. So one of the things we've done recently is covered like limits and the limit laws. And one of the limit laws we had was that for like polynomials and for rational functions, the only thing we have to do is just plug in the limit. Actually turned out to be very nice. And the reason why we can end up doing this is because it turns out these functions are continuous. So what I'm talking about is continuous functions. So let me just try to, define that for you. So our first definition, I'm going to use this for definition. I think some other people use like just DEF. Well, this is how I like to do it. Say a function f is continuous at a number a if the following happens. We say if the limit as x goes to a of f of x is equal to f of a. F of a. In this case, we say the function is continuous. And the reason why is just that we could just basically just plug in the limit into f, and if that's true, then we get it's continuous. So in order to say that, in order for us to have this continuity, we need three things in order for this to be true. So the first one is that f of a has to exist. If the function is not defined at a, then it's not continuous there. The second one is we need that the limit as x goes to a of f of x actually exists. So even if it's defined there, we need the limit to exist, because it's not always the case. And the third one is finally, again, what we just showed, is that not only does the fact that the limit exist, but it has to equal what the function is actually doing at that point. And we say a function is discontinuous at a if it's not true. So let me just clarify. All right, sorry, it's a lot to write out. It's very simply a function is discontinuous if it's not continuous at that point. So just a quick example of a function that it could be continuous. Or let's have an example if we want to try to see if a function is continuous. So we'll say determine if f of x, which is equal to x squared minus x minus 2 divided by x minus 2, and we have 1 here. So again, this is going to be a piecewise function. So this is going to be when x isn't equal to 2 and when x is equal to 2. So we want to determine if this function f of x is continuous at 2. I just wrote x equals 2 just to kind of clarify, but you can just say at 2 as well. So what we have is that the function is actually defined, to be differently at two different values. So the way we needed to kind of go over the fact that to show that a function is continuous, we need that f of a exists. In this case, our a here is equal to 2. So at 2 we get 1. So we have that f of 1, f of 2 is equal to 1. So that's our first thing. So the second one is we need that the limit as x goes to a of f of x actually exists. So if you remember what I just said about, polynomials and rational functions, is that when we actually plug that in, is that the limit does actually exist. So far what we need to in order for it to be continuous is that the limit as x goes to f of x is equal to 1. Because if it's not equal to 1, if it doesn't equal to 1, then it's not equal to f of 2. So let's try to find out what the actual limit is. So let's see, we have the limit as x goes to 0, 0, limit as x goes to 2 of f of x is going to be equal to the limit as x goes to 2 of x squared minus x minus 2 over x minus 2, which we can simplify as, x minus 2 over x plus 1 divided by x minus 2. And I'm just going to kind of clarify that here. Let me cross that out a bit. Sorry, my work is a little messy. So, the x minus 2's will cancel, and that's going to leave us with a limit. I wrote 0. Okay, why am I writing 2? All right, sorry. Limit as x goes to 2 of x plus 1 is equal to 3. Because again, all we have to do is that this is a nice continuous function. It's just a polynomial. We just plug in 2, so all we get is 3. Sorry guys, I'm also recording this at like 4 in the morning. Apologize if I sound a little tired. All right, so what did we get? So we get the limit as x goes to 2 of f of x is equal to 3. But remember, in order for it to be continuous, this does not equal 1, which is equal to f of 2. So the fact is that the function is discontinuous at 2. So since limit as x goes to 2 of f of x, which is equal to 3, does not equal to f of 2, you say f is discontinuous at 2. All right. So now let's move on to the next thing. So the fact is that there's many different kinds of discontinuities. Like maybe there's this case where it's just that the limit here, as we approach from the left and right, actually existed, but the function was just somewhere else. In that case, we call it a jump discontinuity. Well, not a jump discontinuity. We call it a removal discontinuity. So let me write that. Last problem. We have a removable discontinuity. Let me just clarify. At x equals 2. And the reason why it's called removable is because we can fix that pretty easily. And the reason why is because we say because redefining f of 2 is equal to 3 would make the function continuous. All right, so all this means is that, a removable discontinuity is, all right, it's a function, it's not where it's supposed to be, so if we just put it back in a nice position, then we get continuity. It just means like f of 2 or f of the limit point is not a nice spot. All right, so then we have another example of like an infinite discontinuity. So this one actually kind of comes in lines with vertical asymptotes. So this is an infinite discontinuity. Whoops. So an infinite discontinuity is when the function grows unbounded as you let it approach a number. So again, unbounded just means that the function will go to like some positive or negative infinity. So just a quick example of what this might look like is if we take this function right here, and then you say this could be like 1 over x to the 4th. And then what we can do is, once we go to as x goes to 0, we get that the function goes to infinity. I realize my line's a bit squiggly, but you guys will deal. Alright, so this is where I kept on getting the limit as x goes to 0. So here, the limit as x goes to 0 of 1 over x to the 4th is equal to infinity. So this would be an infinite discontinuity at x equals 0. Alright, I just want to clarify something. So the fact that this function is actually not defined at x equals 0 is fine. We can actually modify this point to actually work out. So like we can add the fact, for in this function right here, x can equal 0, but if we wanted to, we could just add a little addendum, I guess. You could, add a point if you wanted. You could say 0 at x equals 0. So this way, like, you still have a vertical asymptote at x equals 0, and you still have this discontinuity, but it doesn't always have to be, like, a function doesn't always have to be, not defined there. We can actually put a point there, and we still have the same things as before. Just a little note. All right. So then our last kind of discontinuity we have is a jump discontinuity, which is what I was trying to say earlier. All right. So a jump discontinuity is basically when the left and right limits don't actually meet, which I think is one of the other cases we've said. It's like, if the limit doesn't exist, that implies, something weird is happening, and something weird in this case would be a jump discontinuity. So kind of what the idea kind of tells you just means that the function jumps as you, from one value to another. And again, I'm going to put jumps in quotations because that's not really a very accurate mathematical word, but it's a good idea to kind of describe what happens. Oh man, I can't write too well. All right. So let me just actually draw an example, kind of like what I just did, for infinite discontinuities. So in the case that I was just talking about, we basically have a function kind of jumps from one value to the next. And, whoops. All right. So if you guys remember the heave size function, that function that, will, let's just say this is 1. This is 1. There's a function that, starts off at 0. Oh my lord. All right, sorry about that. It's a function that goes to 0. It goes to 0 as we approach from the left. And then for everything positive or greater than or equal to 0, it's 1. This is like h of x. So again, let me just clarify. It was 0 if x is less than 0. It's 1 if x is greater than or equal to 0. In this case, we have a jump discontinuity at 0. And the reason why is because that the limit as, x goes to 0 from the right of h of x does not equal to the limit as x goes to 0 from the right of h of x. And I want to clarify that these limits do have to exist in some manner, but if they're not equal, it's a jump discontinuity. So the idea though is even though we have we can say, this is discontinuous, but the fact is that we can also define continuity like what we've done with limits. We can talk about continuity from the left or continuity from the right. All right. So another definition. Say a function f is continuous from the right we'll say at a number a, it's going to be again just a generic number. All right. So continuous from the right at a number a. Oops, that's a bad squiggly line. I think you guys can probably guess what it is. That the limit as x goes to a from the right of f of x is equal to f of a. And likewise, you can do that from the left. Again, continuous on the left at a if, as you guys can imagine, the limit as x goes to a from the left of f of x is equal to f of a. So again, kind of like how we define left and right hand limits, we can also define, left and right, continuity. It's defined just as you expect. The most important part of continuity is just that the fact that the limit as you approach something is equal to a function value at that limit. So like just a quick thing of what we would say about the heave-sided function is that what we actually have is that here we have actually an open circle here. Whoops, I erased that line. So what we actually have is that, the heave-side function would be like right continuous. So and the reason why is because the fact is that as we approach from the right, it's actually, you have a closed circle here. If we had like an open circle, then that would mean it's like not. So just a quick example again, just kind of clarify a bit more. Let's actually draw a graph. All right, example. So let me just try to draw this. All right, so 1, 2, 3, 1, 2, 3, 1, 2. All right, so it's going to start at 1. It's going to go this way. It's going to have an open circle, and then it's going to go to 2, 2. All right, that was a crappy line, but let's just pretend that's 2, 2. It's going to go like this. And then our last dot is going to be at just 1 point above that. Same point, and then it's going to go this way. It's going to be f of x. So I think, as you guys can tell, we have a jump discontinuity at -1 and 2. Again, so here, due to the fact that there's a gap at these values, we have a jump discontinuity at these values. So let me just write that down. All right. So, sorry. I was just yawning. All right. But there's one thing that actually we do have. So we have the limit as x goes to 2 from the right. Again, so this is going to be, this actually as we approach the 2, and we have the filled in circle right here. So this means that f of x, limit of x goes to 2 from the right of f of x, is actually going to be, hopefully that's clear that this is 3, is equal to 3, But again, that's a closed circle with us, so that's actually equal to f of 2. So in this case, we actually have continuity from the right at 2. And another way of saying like shorthand is just a right continuous. Likewise, we can do the same thing for x equals -1. As we approach, -1 from the left, we get that the function approaches 0, and it's actually defined there, so that's okay. Again, so the limit is equal to 0, the function has a closed circle there, that means it's actually equal to that value there. So that means we have, that f is left continuous at -1. All right, so that's actually pretty nice. These examples aren't too hard. It's still like, the idea of limits and all that. But, continuity is the very nice thing that we're talking about. All right. So now let's move on to, Sorry, 1 second, guys. I accidentally messed up my notes I was looking at. Okay. So the next thing we're going to define is, what it means to be continuous everywhere. Like we're not always like continuous at just one point. Like when we talked about polynomials, for example. When we talked about them, we actually said, they're continuous everywhere. So let's go ahead and start with a new definition. What does it mean to be continuous in several places? All right, give me 1 more second. I gotta find my fucking notes. I hate the damn stupid keyboard. Still have got technical issues while I record. All right, okay. All right, okay, finally got it. So the definition is going to be a function f. You say is continuous on an interval. Again, this is going to be like in more than one spot. You say it is continuous on an interval, as you guys can probably expect. If it is continuous, at all points in the interval. Or in this case, you could say every number in the interval as well. All right. So one of the things that we should note is that continuity at the endpoints. Because, if we look at just an interval, this will be like A, B. Continuity to say at A and B just means from the left or from the right. Because we're not going to be approaching the function f of x. We're not going to be approaching b from the right. We're not going to be approaching from outside the interval. Oops. So let me just kind of clarify. So a and b. So this would be a limit as x goes to a from the right of f of x is equal to f of a. And we would have to have the limit as x goes to b from the left of f of x is equal to f of b. So this is kind of generic writing, but that's basically what we would have. You just make sure that the idea that we're like to be continuous at the endpoints just means we could only have to approach it from one place because they're only defined from going from the left or from the right. All right. So some of the ideas that we had from the limit laws, like when we added two functions that have a limit, then we can just, do the sum of the limits instead. All right. Sorry, maybe I said that weird. I don't remember what I just said. All right. So kind of like using the limit laws again. Like, if we added two functions together where they had nice limits, then we could just do the sum of the limits, or the difference. A lot of those nice limit laws we have, we can still extend them to continuous functions. So now is actually we're going to be doing a theorem. And I'm going to kind of clarify that theorems are very nice. I'm just going to mark them in red or something. Theorem. Again, that's kind of shorthand notation for a theorem, is just to write it like that. So we say if f and g say continuous functions, say at a and c is a constant. Again, this is basically just going to be like more limit laws. And we have the following functions are also continuous. And what I mean by continuous, I also mean at the same point A. All right, so the functions are going to be continuous. There's going to be f plus g. Whoops. I hate when that happens. All right, so it's going to be f plus g. We have f minus g. It's going to be c times f. I think it's this way. F times g. And then our last one's going to be f divided by g, but when g of a is not equal to 0. So again, I kind of wrote it a bit vague, but the idea is the sum of continuous functions is continuous. So let me just point it out. So the sum of two functions is continuous. Well, the sum of continuous functions is continuous. The difference of two functions is continuous. If you have a continuous function being multiplied by a constant, again, that's continuous. If you multiply two continuous functions together, you get a continuous function. If you divide two continuous functions, then you still get something as continuous, but only if the bottom piece isn't equal to 0. All right, so what I just said above here is that, a function f is continuous on an interval. And that an interval isn't everything. It's not negative infinity to infinity. And there's some functions that are continuous everywhere, as we would say. So let me kind of clarify what, functions are very nice. Functions that are continuous basically everywhere in their domain. So again, this is going to be another theorem. All right, so the first part is any polynomial is continuous everywhere. All right, so again, just for, kind of for clarification, I realize my handwriting is bad again. I really hope you guys can read my chicken scratch. Sometimes it feels like a little actual chicken is scratching. All right, so it's continuous everywhere, and everywhere just means we say, the notation would be like negative infinity to infinity, but you guys are in calculus now, you're going to be using some new notation. The way the notation we would use is R. So when I say, we're continuous on R, what that means is just the real numbers. That's what the R stands for. The last one is, the second part is going to be a rational function is going to be continuous on its domain. So the idea kind of comes from, if you take two polynomials, if you take two polynomials that are, nice, they're going to be continuous everywhere. If we divide one by the other, then we're also going to get another continuous function. Oh, just wherever when it doesn't divide by 0. Oops, I forgot to say rational function. I am dumb. All right. So again, so this is just saying, if we divide by like x minus 3, it's not going to be continuous at 3. Kind of duh. All right. And also, like, these aren't the only functions, So let me just kind of clarify. There are more functions that are continuous of their domain. So I'll need that down more red. So more functions. So again, just to say that over the domain just means if we can naturally plug it into the function, then it's continuous there. So we will say, whoops. So this would be like root functions. So, like to the nth root of something, like, square root, cube root, 6 to the 7th root. Trig functions are, so what that means is like sine and cosine are continuous everywhere. We have inverse trig functions. Those are also continuous everywhere. Well, on their domain, I think trig functions are, you have to specify sometimes. Exponential functions. So like e to the x is continuous everywhere. And the last one we have for now is just logarithmic functions. So far, it doesn't seem like it really said too much, but actually this is pretty nice. What this tells us is that any combinations of these functions, whether or not they're being multiplied, divided, subtracted, added, they all are continuous. All we need to do is, if we take an arbitrary function, if we can split it up into root functions or trig functions, then we can say it's continuous. It's very nice. So let me just do an example real quick. So let's consider, let's evaluate a limit. If you want to evaluate, oops, I can spell evaluate right. So the limit as x goes to 2 pi of sine of x plus 1 divided by 3 minus cosine x. We want to evaluate that limit. So kind of what I just said is that we have trig functions are continuous. In fact, everywhere they're continuous. If they're continuous on their whole domain, we can plug in 2 pi into sine of x and cosine of x, and we get actual nice numbers, so it's pretty nice. And one of the things we should note is that we don't actually divide by 0 here. Cosine of x is never going to be it's always between -1 and 1. So, well, actually, let me just go ahead and clarify some of the steps I've said so far. So we have sine of x plus 1 and 3 minus cosine of x. What the heck? Alright, that was weird. Alright, my bad, guys. Technical issues as always. Alright, so we have sine of x plus 1. And we have 3 minus cosine of x are both continuous at 2 pi. And this kind of just comes from the previous thing that the previous theorem, that trig functions are continuous on their domain. You can plug in 2 pi into both those things, and therefore still continuous. And the only thing we need to do is verify that this is never equal to 0. So as cosine of x is always between, let me just write it out as -1, cosine of x, 1. So as cosine of x is only between -1 and 1, it could never equal 3. So this means that 3 minus cosine of x is always greater than 0, but that's just a fancy way of saying if, never equals to 0. And because of that, what that actually tells us is that we can use the previous theorem some more. So like you could say like a rational function, or we could appeal to this fact right here. The fact that f divided by g is continuous. Specifically when, g of a is less than equal to 0. And again, we just showed that, whenever we plug in sine of x, whenever we plug in like 2 pi into 3 minus cosine of x, we definitely don't get 0. So this shows that sine of x plus 1 divided by 3 minus cosine of x is continuous. And therefore, we can just plug in 2 pi. So let me just go ahead and do that. So we have the limit as x goes to 2 pi of sine of x plus 1 divided by 3 minus cosine of x is equal to the limit as, again, I was going to kind of clarify what the definition of the limit is. So I'm just going to call this f of x, which is equal to f of 2 pi, which is equal to the sine of 2 pi plus 1 divided by 3 minus cosine of 2 pi, which is just going to equal to 1/2. So therefore, the limit we got is just 1/2. So what we did in this problem was we explained why the top and the bottom are both continuous functions, and we showed why the bottom function is never 0. Or at least if it is equal to 0, then it's not where we care about. So in this case, it is continuous at x equals to 2 pi, so we could just plug it in. It's pretty nice, actually. So there's another way of doing continuity. So what we did here was, we did, not composition. We did addition, we did subtraction, we did multiplying by constant, and we did, multiplication and division. So we all have those things whenever we do them in terms of functions, in terms of continuous functions, specifically, whatever the heck that word is. We still get continuous functions. So basically, this is saying, continuous functions are nice, but they get nicer, actually. So another theorem, which kind of tells us how nice continuous functions are. I love continuous functions. So another theorem so if you have a function that is continuous, I'm just going to use some shorthand sometimes if I'm feeling lazy and I don't want to write the word continuous, but I'll do it right now. So I might write cont like that, just for abbreviation sometimes, but I'll just keep like this for now. Say f is continuous at a number b, and we have a function g of x. Where the limit as x goes to a of g of x is equal to b. So this is very important. It's the fact that f is continuous at b, g of x is going to b. Then what we have is the limit as x goes to a of f of g of x is equal to f of b. So what this basically tells us is that we can basically move in the limit. So let me just kind of clarify what that means is that this is one of the really nice properties of continuous functions is that we have the limit as x goes to a of f of g of x is equal to the limit, well, not the limit, but f of the limit as x goes to a of g of x. So basically what this means is that we can take this limit and actually move it inside the function, which is actually pretty nice. Because another way we can see, the continuity as, which honestly when I first saw it, I was like, wow, this is awesome. Another way you can see continuity or define continuity likewise is you say the limit as x goes to, like, say, b of f of b, well, not f of b, of fx is equal to the f of the limit as x goes to b of x. Let me just write this nicer. So that's another way of seeing that continuity is defined. Is basically what that means is we can take the limit, put it inside the function, and then just plug it in. Because this right here would just be f of b. Because this right here would just equal to b. And that's just one of the limit laws. Well, that's just a little fun fact for you guys. It doesn't matter so much. All right, let's keep going. Let's do an example. All right. So let's just say we want to evaluate a limit. Say evaluate so the limit as x goes to pi of sine of x plus sine of x. Again, this looks pretty gnarly. I don't like it. But what we should note is sine is continuous. And it's going to be continuous for all x. And we also note that x plus sine of x is also continuous, so then we can actually move in the limit. We'll put past the limit on the inside, is what some people say. So we have the limit as x goes to pi of sine, what the heck was that? Just flashed yellow for a second. Sine of x plus sine of x is equal to the sine of the limit as x goes to pi of pi plus sine of x. And this will be equal to the sine of, so, whoops, that's not supposed to be a pi right there. You guys probably saw that and be like, what the heck is he writing? Thanks for doing that again. So this is supposed to be an x right here. So again, going from this step to this step, all I did was move the limit on the inside, and now we're actually going to take the limit. And again, we can just use the limit laws for this one, or use the fact that both x and sine of x are continuous, and we can just plug it in. So we just get sine of pi plus the sine of pi, which is just equal to, the sine of pi is equal to 0, so we just get the sine of pi again, which again is equal to 0. Because this right here is equal to 0. So that's pretty nice. All right, so again, we have another theorem. Unfortunately, this section just has a lot of theorems in it. It's gonna be kind of annoying, but all these things are pretty powerful when we actually do math. Whenever it comes to, solving problems or, just doing math, we could appeal to these theorems to talk about things that are complicated. So let me just talk about one of those theorems. All right, so let's have a continuous function g. It's going to be continuous at a point A, at A, and f is continuous at g of A. And what we have is as a composite function, we have, f composed with g, which is given by, I think, if just in case you guys haven't seen the notation in a while, which is f composed with g, we would say at x, which would be equal to f of g of x, is also continuous at A. So essentially, a continuous function of a continuous function is a continuous function. Yeah, it sounds whack. But basically the idea is we can plug continuous functions into another one and also just get a continuous function. So just an idea of how we could, just argue that real quick. Let's just take a quick example where we could verify if a function is continuous. We take f of x is equal to the sine of x squared. We say g of x is equal to x squared, and h of x is equal to sine of x. So then x squared is a polynomial, so it's continuous. And we also have sine of x is equal to a trig, a trig function, so also continuous. So that means that f of x, which is equal to h of g of x, is also continuous. And that's what I mean by a lot of these things can be pretty powerful. We can take something that looks a bit complicated, try to write it, in terms of something else, or in terms of nicer pieces. In this case, our pieces that we chose were x squared and sine of x. And those were actually pretty helpful. And one of the things I should notice is that, kind of clarifying with like the notation that we used earlier, that polynomials are continuous everywhere. So you could say on R, again, the real number is negative infinity to infinity. Sine of x also continuous on R. So we say, so the function f of x is also continuous on R. Again, where R is equal to negative infinity to infinity. And this is also shorthand. A lot of us don't like to write, negative infinity to infinity. You guys can kind of tell my R's look better than my infinities, so prefer my R's. All right, so we have one last pretty powerful theorem for us to go over before we end this section. And this one is honestly sexy. I love it. It's called the intermediate value theorem, or IVT for short. And I'm going to write the name in red. So it's going to be the intermediate value theorem. All right, now let me actually write what it is. So the first thing that we need is a continuous function on a closed interval. Say, suppose that f of x is continuous on AB. I want to specify that this is a very technicality. When I say closed, it means including the endpoints. So closed interval AB. And the fact that these are brackets, including A and B, is very important. If we don't have that, then we don't have the intermediate value theorem. And now let's keep going. And let n be any number between f of A and f of B. Man, my handwriting is trash. All right. So what this means so far is that, we have a function that is continuous on a closed interval. So it's an interval including its endpoints. And we have some number in between, the values at the endpoint. And just to make things easy, because, if this is the case, then it's something else. But you have that f of A does not equal to f of B. We can have f of A equal to f of B, but it doesn't really provide us useful information. It's not something that we could use the intermediate value theorem for. You would have to try to do something else to appeal to it. All right, so far the setup is we have a continuous function on a closed interval, so it includes the endpoints, and we have a number n between f of A and f of B, and these numbers aren't equal. So then what do we get? We have then, say there exists a number C C such that, or not in C, but we have C in AB. Again, this is going to be the open interval now. So not including A or B, such that f of C is equal to n. All right, so what does this mean? Let's draw a picture and I'll show you. All right. So there are going to be a few different cases we can do this, and let me try to do that. So the first picture we can draw. Let's consider this A, consider this B, and then we continue this point right here to be f of A. And again, I'm just keeping these things arbitrary because we don't need them to be specific. And then let's do this. So again, our setup is so far is fine. A continuous function on a closed interval, AB. So here's AB. It's defined on the intervals. And we have that f of B and f of A are not equal to each other, so let's choose an n. Just n be an arbitrary number there. And then what the theorem tells us is that if we look at the values for n on the function, hopefully it's a bit clear, that this will actually correspond to a point on the graph of f of x, and will actually be C. So the fact is that we'll get f of C is equal to n. So again, in this case, this function was increasing, so f of A was greater than f of B, but we can have the situation reversed. We didn't need to specify that one endpoint had a value greater than the other. Here, let's just do A, let's do B. Let's put all A up here this time, so this will be f of A. Here, this will be f of B. Put this right here. So what we can do now is just this. All right, let's just pretend my graph looks great. All right. So again, this will be our f of A. This will be our f of B. If we choose an arbitrary point in the middle, n, then that's going to match up to a point on the graph. And then we can just look down at that x value, and it's going to be, we call that number C. We just say f of C is equal to n. That's because of that theorem. And this is just a property of just like continuous functions. Continuous functions, like the way you can say continuous function is if you can draw it without lifting up your pen, then it's a continuous function. And that's pretty nice. And this intermediate value theorem is actually pretty strong. It's pretty powerful when it comes to a lot of things. And we specifically use it in a lot of like root finding algorithms. If you ever heard of like the bisection method before, it's definitely has a lot of applications. So let me actually demonstrate an example of how we can use IVT. So we can use it is to show a function actually has a root in a specific interval. So let me just write that down. We can use IVT to show a function has a root. I want to clarify it's in a specific interval because, to have a root, which is not very helpful, we kind of have to specify where the root is. And that's one of the parts of the IVT, is we need to have somewhere we're doing this. So, let's talk about a function that actually, has this work. So let me just draw the graph of, what kind of situation I'm talking about. This will be f of B, and this will be x, this will be y, this will be f of A. Call this A, call this B. So again, so far what we have is a continuous function f of x. It is defined on its endpoints from a to b. And we have that the values are different. And one of the things we should notice is that this line right here is like 0. This is y equals to 0. So we have f of b is greater than 0, which is greater than or equal to, oops, not f of b. F of a is greater than 0, which is greater than f of b. Because f of b is negative, f of a is positive, so they're definitely not 0. So again, using the intermediate value theorem, if we just let n is equal to c, then we can just, go over, look at that point. And then that value right there is our 0. So we have that f of c is equal to 0. So this is pretty nice. So the only thing you need to show that a function has a root is just show that at one endpoint it's positive, at another endpoint it's negative. And that's pretty nice. And also there's one other thing that we can say, is that this actually doesn't even clarify, if it's multiple times or not. It just says that it needs to happen at least once. So let me just draw an example of where this function could, have this happen. And this idea is that, basically is like what goes up must come down, or in order for you to go to school, you basically have to go somewhere in between. And the intermediate value theorem doesn't tell us, how many of these possible points that we could have. It's just that there has to be at least one. If you never cross if you never cross 0 and you're continuous, then you have some issues. You're doing some magic. So again, this doesn't always help us find what that number is. It doesn't always help us, and it's actually equal to 0, but it doesn't actually tell us what these values are. It just gives us the idea of their existing value. It just says there is 0, there exists a value with this property, and that's it. So now let's just do another example, but without a graph. Let's do some actual math. And then that'll be the last example for the moment. So example, so use the IVT. And to show that there's a root of the equation you could say root of this equation, or you could say solution, if you would like, of the function the key root of x is equal to 1 minus x on the interval, or not on, you would say in the interval 0, 1. So typically whenever I give you the interval like this, that basically just tells you the endpoints. But remember in the intermediate value theorem, we talked about a specific function f of x. So how do we construct the f of x? Say that we have the key root of x is equal to 1 minus x. So that means we want, the key root of x plus x minus 1 is equal to 0. I just moved everything to one side. And then we have to choose our f of x to equal to cube root of x plus x minus 1. So the 0 of that would be the solution here. All right, so you should note that f of x is just a continuous function. Well, is a combination of a polynomial and a root function. All right, so we have root. This is polynomial, so f of x is continuous on R. All right. So because it's continuous, we can keep going now. So now let's actually try to plug in, f of 0 and f of 1. Let's try to plug in the endpoints. So we get f of 0 is equal to the cube root of 0 plus 0 minus 1, which is equal to minus 1. And we have that f of 1 is equal to 1 plus 1 minus 1 equals to 1. All right. And now, remember what we did for the previous thing, when we talked about how we can use it to find a root, is that one of the endpoint has to be positive, another endpoint has to be negative. So what this at 0, it's negative, at 1, it's positive. So, since f of 0 is less than 0, which is less than f of 1, we have to say, since we have this inequality, since f is continuous on AB, well not AB, on 0, 1, by IVT, we know that there exists number C, and exists number C in 0, 1. Sorry, it's a lot of words to say. Such that f of C is equal to 0. And in IE, what that means is that, there the Q root of C is equal to C minus 1. And that just means it has a solution or at least a root. All right, so let me just kind of reiterate what we did. So we wanted to use IVT to show that this function has a root. Well, in this equation, we say it's an equation, but we rewrote it to look like this. As something equal to 0. We call that a function f of x. We noted that f of x is a root function plus a polynomial. This particular root function and polynomial are continuous everywhere, so the sum is continuous everywhere, so f of x is continuous everywhere. So then we plugged in f of 0, we got that it was negative. We plugged in f of 1, and we got out it was positive. And since we get the fact that one's positive, one's negative, and the fact that it's continuous on 0, 1, including 0, 1, we can use IVT to show that there exists number C in the open interval 0, 1, so somewhere between 0 and 1, such that, f of C is equal to 0. Or, it has a root in 0, 1, however you want to say that. But that's pretty nice, actually. That's how we use root finding algorithms, actually. It's a lot of computational math, but that's it for this section. Sorry, it was pretty long. Covered a lot of theorems, but they're pretty powerful theorems, pretty beautiful theorems. Hope you guys enjoyed it. Good night. Like, comment, and subscribe. Hit the bell icon, I guess.